We are live. Welcome back. This is part 2 of our Organic Chemistry Rapid Review. It is the same day. It's literally been 2.5 minutes. For anyone who's watching this out of order, please finish up the entire Organic Chemistry playlist before you watch this video. Because as I can tell by the faces in the room right now, we are tired, and this is a lot of information. You need a very good background in MCAT Organic Chemistry before encountering this lecture. So if you haven't already, please go study Organic Chemistry first. I have a whole playlist, or study out of the book. Do whatever you have to do. Thank you. And check the link in the description for all of the stuff associated with this lecture program and the links to all of our lectures all over the place. Like and subscribe. One of my, like and subscribe. I don't know, it's buy me a coffee. Actually, no, I on recommendation of one of my students, I started a buy me a coffee page because it's just like, oh, like people would want to support or whatever. Like I get messages. Huh?
Did they buy it for you?
I mean, no, I haven't put it anywhere yet. I just started the page. But what I'm going to do is when I actually start advertising for it, I think I don't expect a lot of people to actually, because we're all students. Like, I'm not starting it because I want to make money off of it. It's just like people are like, oh, well, we want to support the channel, blah, blah, blah. You want to support the channel? Yeah, buy me a coffee, whatever, right? But what I'm going to do is 50% of everything I make, I'm going to donate to a charity that we're going to vote on every month. So I'm going to send out an email. We're going to vote on what charity we want to donate to, and 50% of whatever comes in through Buy the Coffee will go to me, and 50% of it will go to a charity of our choosing.
That's very nice.
Okay? So it's a way of mobilizing our viewer base to a good cause. And it's a way of me to also survive through medical school. Okay. So the first part was just nomenclature, R, S, blah, 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 all those considerations, SN1, SN2, et cetera, et cetera. Things that an Organic Chemistry 1 student would be comfortable with. Now here are some things that an Organic Chemistry 2 student would be comfortable with. Let's talk about alcohols. So, the classic reaction that comes up on the MCAT with respect to alcohols is a dehydration. Right? Now it depends what type of alcohol you have. That's going to dictate what kind of dehydration and what kind of mechanism is going to take place. So let's look at primary alcohols and secondary alcohols and tertiary alcohols, right? So for a primary alcohol, like this, right? The way we do the dehydration, we usually, normally, most of the time, do a acid-catalyzed dehydration, right? So these are acid-catalyzed reactions. And we'll talk about what acid-catalyzed means when we go through them. So we're going to do H+, right? Or, actually, how do I want to do this? Yeah, we can do like, dissolve this in water and a catalytic amount of H+, right? And the reason we're going to use water, I'll show you in a second. So the first thing that's going to happen is that's obviously going to form hydronium, right? The combination of water and H+. This is going to pick that up, and we're going to get 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That. It's a pretty good leaving group, right? And now we have a hydrogen right there and a water molecule that can come and grab the hydrogen and fold this down and fold that up, and we get 1, 2, 3, 4, 5. Dehydration. How is this acid catalyzed? Well, you see, when the water picks up the H that does the elimination, we reform a molecule of hydronium. How did we start the reaction? We started with hydronium. So the starting material comes back in the end, and that is a catalyzed reaction. Why did we use water? Well, let's say the flask decides to get a little freaky and says, you know what? Fuck you and your reaction. I'm going to do what I want. And at this step right here, the flask is like, I hate this student person doing this reaction. I'm going to do a really weird SN2 reaction instead. Yeah, good luck with that one, buddy. Good luck. Because what just happened? Nothing. So when the leaving group is a water molecule and use water as a solvent, even if you get some background substitution, it creates the same thing you started with. Right? That is why, for this reaction right here, for my advanced organic chemistry people who have been following along for a very long time, for this reaction right here, what's the base we use? Sodium ethoxide. So that if it substitutes here and tries to kick off, it creates itself. So the reaction won't progress until it abstracts that hydrogen right there. Because if we use OH, it would eliminate and deprotonate and eliminate and deprotonate, and you'd kill the whole reaction. We'll look at that later. So that is primary alcohol dehydration. What sort of reaction is that? Out of SN1, E1, E2, SN2, what reaction is that? That is an E2. That is an E2 elimination. Very good. So primary alcohols dehydrate through an E2 elimination. A secondary alcohol, when you protonate it, so let's say plus H plus, OH, H, can that guy leave? Of course he can. And now, boom. What sort of mechanism is that? That is a E1. Also, right? What did the protonation here? H3O plus did the protonation. You reform H3O plus at the end, acid catalyzed.
How can you tell if it's E2 reaction?
E1, carbocation. E2, non-carbocation. Tertiary, I'm going to put it up here because I don't want to reach down there. Protonation with H3O plus. Leaves on the ground. Oops. E1. Yeah.
So it's not just because it's a carbocation, because in the E2 it's primary, so it won't form a carbocation. That's the reason.
Exactly. Out of these three, which is the fastest? Primary, secondary, or tertiary? Tertiary. It's the most stable. The carbocation is the most stable. This, you need quite a bit of heat for the primary dehydration. And that's a big question on the MCAT. Actually, you know, between the primary and the secondary and the tertiary, the primary might be a little quick because it doesn't go through a carbocation, possibly. But on the MCAT, they're going to ask you like a bunch of substrates, like a secondary. One of them is going to be tertiary. The tertiary is always the answer for the quickest reaction because it's the most substituted. The carbocation is the most stable. Whenever they ask you about the quickest rate of reaction, you have to ask yourself, which of these has the most stable what? The most stable transition state. And since the carbocation is the transition state of the tertiary dehydration, whichever has the most stable carbocation is going to be the fastest reaction.
What's the transition state for primary?
Whatever the fuck this is.
Gotcha.
I realize that like when I rewatch the lectures, sometimes you guys ask questions and the audience doesn't hear them, and I forget to repeat them. The question was, what's the transition state for the primary? And it's whatever the fuck this is. That's dehydrations. Are we good?
Yep.
All right, moving on. Where are Kiro and Sarah? Are they dead? It's very unlike them to miss a lecture,
Yeah. It's 2 in a row now.
right? It's crazy. I missed a couple lectures.
Yeah.
I like to imagine that you guys like go home and cry when I say I'm not coming, but I know you guys are just like so excited. You're like, oh my god, I can go home at a reasonable time.
No, you're right. I cried.
You're the reason why I touch grass every day.
Let's go.
Grass.
You're like, I can leave my desk. I don't have to hear my keyboard clacking anymore. All right. Jones reagent, what does it do? It oxidizes up to the top position that it can. So the aldehyde will go all the way to the carboxylic acid. The alcohol goes all the way to the carboxylic acid if it's primary. A secondary will go to a ketone, and a tertiary will not oxidize because there is no position for it to oxidize on. All right, so we're not going to go over that.
Is that because there's no beta hydrogens?
Well, it's because a tertiary alcohol, if you wanted to oxidize it, you'd have to do this, and that is a grave sin. Satan himself will appear behind you and lick your asshole if you make that sin. I'm not kidding. It's happened to me before. One more thing. Very important consideration here. What's this? A quinone, right? Well, wait. Is this a quinone? I think it's oxidized. It's the quinone, right?
Yeah.
Hydroxyquinone. So this is a hydroxyquinone. And if you add Jones reagent here, it's going to oxidize. And what do we get? We get the quinone, right? So the quinone is this guy. Silly little guy. And where's this implicated? The electron transport chain. This is QH2, and this is Q. So when NADH and FADH2 come to drop off their electrons on iron-sulfur cores instead of complex 1, complex 2, those iron-sulfur cores pass off the electrons up to Q and turn it into QH2. They turn Q into QH2. Now, this is not the entirety of coenzyme Q. It is a massive compound of which one domain is this. It is huge, but this is the active domain of coenzyme Q. Question was, coenzyme Q and ubiquinone are the same thing? That is correct. For your purposes. Mesylates and tosylates, we went over already, right? It's the way of making a leaving group from an alcohol on the same side of the alcohol. So let's do a tosylate. You guys just see me like lag? I just like fucking freeze for a second when I put the double bond in the wrong position. All right. Boom, bam, bop, pow. Right? And then normally when you do this, you put a little bit of pyridine in the flask. What is pyridine? It's this guy. And the pyridine's gonna deprotonate this and make pyridinium. And you get this. And since this is a tosylate, this can be rewritten as OTS. And how is that a good leaving group? Well, when you make it leave, the oxygen leaves with its electrons. And now the oxygen is absolutely free to resonate into these two oxygens as well. And that's a very good leaving group because it's resonance stabilized. And the chloride just goes away and connects with the pyridinium now. So the pyridine becomes pyridinium. And the chloride hooks up with that, so you get pyridinium chloride as a waste product. Why is that called pyridine? Well, pyridine is the backbone of the pyrimidine nitrogenous bases because they have one ring. It's almost like science makes sense. Nah, it's not real. It's propaganda.
It's all made of, anyways. She's not sure what it is.
Aldehydes and ketones. We just talked about the oxidations, right? The reductions, if you reduce a ketone, it'll turn back into a secondary alcohol. If you reduce an aldehyde, it'll turn back into a primary alcohol, right? You can do that normally with LiAlH4, lithium aluminum hydride, right? Which is different than sodium hydride. Very, very different. Very different. Not the same thing at all, right? Now, the important thing here was what? You take this and you put it in a solution of water and a little bit of acid. What's going to happen is that you're going to get a protonation step that happens with the hydronium. Let's just draw it out, right? Since people like mechanistic drawings so much. Also, I'm drawing fast because you don't necessarily need to be taking this down. I just want you to look and process and learn. Right? You don't everyone puts their pens down. You don't need it's a rapid review for a reason. You don't have to be like I know I draw fast. I've been doing this for 4.5 years now. So yeah, you don't need to keep up. It's totally fine. Right? So we're going to get the protonation of this aldehyde, and that protonation is going to allow for a what? Partial positive over there. That partial positive can be attacked by the water. It's a Lewis acid-base reaction that's going to flip this up, and that's going to make OH and OH2, and then a deprotonation with water will form what? A geminal diol, or an aldehyde hydrate. And a ketone hydrate would be the same thing, but the H replaced with R. That H, that H, that H, that H. Replaced with R. Very good. Now, if we replace the H2O with ROH, nothing changes except right? And then now this is a hemiacetal. What are you so happy about?
I remember. Giving me nightmares at work.
And then if you do this reaction one more time, how do you do the reaction one more time? Well, there's a specific step you have to take in order to do the reaction one more time. Take the hemiacetal, remove it. Well, don't remove it from the flask. Like, you can stay in the flask, but now what has to happen is this. Why did I write R? Remember, we swapped to the alcohol. Now it's an acidified alcohol. This guy deprotonates that, makes this. This is a process called assisted leaving. Not assisted living, assisted leaving. electrons come down and kick off a group on the same carbon, because that's a good leaving group, right? This is very reminiscent of that. It's the same thing, but we replace that H with an R. What's going to attack? The water we just kicked off or the solvent? The solvent, because it's in excess. There's like maybe one molecule of this per molecule of reactant, but there's trillions upon trillions of molecules of solvent. So solvent reacts, and we get H, O, R, H, and OR. And then ROH, once again, the solvent, will deprotonate this positive alcohol adduct, and we will get a full-blown acetal. No more hemi, no more half. This is a full-blown acetal. Good? I wonder how many people, this is like the thought that comes to my head while I'm like teaching. I wonder how many people are sitting at home watching my YouTube lectures being like, fuck this guy and all this information, god damn, like start sobbing at their computers. That's you. It'll be okay. You'll be fine.
That doesn't help them.
No, I'm serious. I was there at one point. I was sitting. That's the thing, right? That's the thing that I always have to emphasize, that I was you at some point. That I got a 499 on my practice exam. And I studied all of content and then only went up by 4 points. And I hit that wall in the middle of my content where I wasn't making any progress. And I cried my eyes out at my desk every single day because I was overwhelmed with the information. And I had to make myself a study guide. And I had to wake up at 7 in the morning every day to study. And I said no to hanging out with my family and my friends and my parents. And I missed weddings and I missed events and I missed parties. And I completely isolated myself. And I gained 20 pounds while I was studying. And I got really depressed and I let go of all my hobbies. That was me. That was me. So if it was me and this is me now, you'll be fine.
So inspirational.
Yes, I gained 20 pounds while studying for the MCAT. I'm a stress eater. That's what I am. I'm a huge stress eater. What's up?
20 pounds of knowledge.
Exactly. right to the dome. 20 pounds to the dome, baby. All right. So the next reaction, pretty self-explanatory because we just went over like the aldehyde, the acetal and the hemiacetal formation. This is basically the same thing, right? So let's say we have a ketone right here, and we put it in a solution of NH3 with a little bit of catalytic acid, right? So when it protonates, it's going to protonate with what? It's going to protonate with NH4+, right? So we're going to do plus H+, and we're going to get this guy right here, and then we're going to do this, and that can attack like that, and then this, and eventually we're going to get a little swap, a little scoop diddly whoop, right? And this is going to end up over here. Why? All right, so this also requires quite an astute knowledge of organic chemistry or memorization of the pKa table. You have to know that the pKa of water is 15.7 and the pKa of ammonia is 9.4. Right? So knowing that, you also know, you have H2O, and then you have this, and then you have H3O plus at a 0, right? So understanding this, you can kind of understand how the nitrogen is more comfortable being protonated. So when we do this step, to remove the water, and we displace the positive charge from the oxygen to the nitrogen, That's favorable. That's a favorable removal. Because the oxygen is less comfortable being positive than the nitrogen is. Yes? And what's another way to prove that? BCNOF. Oxygen has higher electronegativity. Nitrogen's more comfortable being positive. Yes? Cool. Okay. Now that, once again, can get deprotonated by this and make, what is this? What did we call this? This is called an imine. This is called an imine. How you doing, boss? How are you?
That's my friend. They just want to sit and
Come. Come to the front.
they're not studying for the MCAT.
Oh, that's fine. You can still come to the front. So that is called an imine, right? And in the same sense that we can have keto-enol tautomerisms, we can have imine-enamine tautomerisms. So the formation of an enamine, you can take an imine, right? And basically, you can do acid or base catalyzed. So let's do an acid catalyzed reaction. So let's add H+, and we're going to do this, NH+, and now let's do NH4, NH3. So now when the NH3 goes, we get enamine. Enamine tautomerism, right? Same thing as keto-enol tautomerism, which is something we've talked about plentifully, right? You want to do a keto-enol tautomerism, swap the N's for O's, and you're good. All good there? All right. End part 2.